Our learning objectives are: for a given temperature and composition, use phase diagram to determine the phases that are present, the composition of the phases, the relative fractions of the phases. We will discuss two types of phases. One is unary phase diagram, the other is with respect to binary phase diagram. And compositions, we will discuss basic composition of carbon in iron. We call it iron carbide diagram. The relative fraction of the phases, in this part we will discuss the different parts percentage wise carbon composition to iron, and the formation of different components at different temperatures, and formation of different phases in the types of phases. We will discuss these in this in detail. Components and phases. Components: the elements or compounds that are mixed initially, for example aluminium and copper, which can be mixed initially. Phases. A phase is a homogeneous, physically distinct and mechanically separable portion of a material with a given chemical composition and structure. For example, the chemical composition and structure for the solid solution is represented by alpha and beta. If we look at the microstructure of both the solutions of aluminum and copper, when they are mixed together, we can get the microstructure of beta, which is this one, the lighter portion, the lighter phase over here and over here, and surrounded by some darker phases, which is alpha. The alpha solution represent the one component, the beta solid solution represent the other component. When they are mixed together, they can mechanically, their properties are improved mechanically. Effect of temperature and composition. Changing temperature can change number of phases. For example, the path A to B in the given copper nickel system. Again, we can explain the copper nickel phase diagram in order to explain about the effect of temperature and composition. If we change temperature, then the temperature can change the phases. If we look at the path A to B, in path A, initially the solution was a solid solution, FCC alpha solid solution. If we give the temperature from this point if we slightly increase the temperature, the solidus line is crossed. Above the solidus line, the melting occurs, melting starts, and above the liquidus solution, above the liquidus line, at this temperature, the liquefaction started, while at point B the solution is completely liquid. So by increasing the temperature, the phases can be changed. Changing composition. CO represents composition. Changing composition can change number of phases. Path B to D is the line for the which represents the change. Changing the composition will result in changing the phase. If at point B, at a given temperature, if we change the composition, if we increase the amount of nickel by weight from 40% to about 70% by weight of nickel. Then the composition from the liquid is starting so that it cross the liquidus line, and the solidification starts, and at point D the mixture of liquid plus a solid solution is resulted by changing the composition of the liquid. So temperature and composition are two variables where we can change the phases. If we change any of the variable, we can change the phase. Microstructure. In order to define the different phase components at different temperatures for the iron carbide diagram, it is necessary to discuss about the microstructure. So we will define some basic concepts with respect to phases and microstructure. We will discuss binary isomorphous systems and what is binary eutectic systems, and binary systems with the intermediate phases and compounds. After we will discuss this, it will be easy for us to discuss about the iron carbide microstructures. In metal alloys, microstructure is characterized by the number of phases, their proportions, and the way they are arranged. The microstructures depend on alloying elements, because when they are mixed, the two components are alloying elements are mixed with each other, their mechanical properties are enhanced, and their microstructure is changed. The concentration, suppose if the same two elements are mixed at different compositions, heat treatment. The heat treatment depends upon the temperature, time, and rate of cooling, like quenching, their quenching effect, or different rate of cooling. The properties of an alloy depend not only on the proportions of the phases, but on how they are arranged structurally at the microscopic level. Thus, the microstructure is specified by the number of phases, their proportions, and their arrangements in space. For example, this is the microstructure of cast iron. This is an alloy of iron with 4% weight by carbon. And how can we explain? There are different microscopic physical properties at 50 micrometer resolution with the help of electron microscope. These are the long flakes of carbide. So these are the long flakes of carbide. So the phase diagram will help us to understand and predict the microstructure, like the one which is shown in the figure. Construction of binary phase diagrams. We can also call it isomorphous phase diagrams. This is a two-component system. Binary phase means two-component system diagram. In this phase diagram, the temperature and composition are variable parameters, and pressure is held constant, which is normally at 1 atmospheric pressure. Temperature is taken on y-axis, and various compositions of two components are taken on x-axis. Examples of binary phase diagram are nickel, copper, gold and silver, chromium, molybdenum, and similarly some other binary phase diagrams which will be discussed. Determination of phases present. For this one, we want to know about, in order to know about the determination of phases that are present in unary or binary phase diagrams, we must know about the one rule, that is, if we know temperature and composition, then we know how many phases are present. So again we will repeat the copper nickel phase diagram. In this copper nickel phase diagram, the liquidus and solidus lines are plotted. So we want to discuss one example in which a point A and B are present. We want to know about the temperature and composition of these 2 points. The first example is when we look at about point A, if we plot a horizontal line towards the left hand side, we will get the temperature of point A, which is 1100. Similarly, if we draw a line downward, we will get the composition of that point A. A is 60% by weight of nickel, and its temperature is 1100. What will be we know about the phase of type of phase of point A. So that will be in what phase. This is the A is an FCC solid solution. Alpha is represented by the solid. Similarly, if we look at point B, if we draw a horizontal line B, we will get the temperature which is 1250 degrees centigrade of point B, while this is in the region of mixture of a liquid plus alpha region in the phase. If we draw a vertical line, we will get the composition of that point B, which is 35% by weight of nickel. So overall, in this copper nickel diagram, how many phases are present? Phase 1 is liquid solution. About liquidus line, we already know about the liquidus line. Liquidus line is the line is the temperature where alloy is completely liquid. Below this line, solidification or a mixture of solidification begins. What is the solidus line? The solidus line, a temperature where alloy is completely solid. Above this line, liquefaction. Above this line, liquefaction begins. So solidus line, and below this line completely solid. If we look at the solidus line, this is the solidus line. Above this line, liquefaction begins, and if we look at the liquidus line, above this line, the solid is the mixture is completely liquid. Below this line, solidification begins. while within these region, within the liquidus and solidus region, the mixture, we can see a mixture of liquid and solid solution. So here we want to discuss about a melting point of these two components. One component is copper, the other is nickel. The melting point of the copper is 1085 degree centigrade, while the melting point of nickel is this one. The melting point of nickel is 1453 degrees centigrade. Above the 1453 degree centigrade, the nickel solution becomes completely liquidus, while below this melting point, the nickel solution is solidus. Similarly, we can demonstrate about the copper melting point. So both are mixed together. The weight percentage is mentioned in horizontal line, while temperature is added and shown in vertical line. For description of binary phase diagram, for all combinations of temperature and composition above liquidus curve AB, the mixture is in the liquid state. This is generally this is the liquidus line. Why we call it liquidus line? Because it separates a liquid phase from a mixture of solid plus liquid phase. And above this line, liquidus line, the mixture is in the liquid state. What is liquidus temperature? Liquidus temperature is the temperature above which a material is completely liquid. Because of liquidus line, above liquidus line, all the mixture is completely liquid. So above this temperature, the material is completely, it is called a liquidus temperature. Solidus temperature. Solidus temperature is the temperature below which alloy is 100% solid. What should be the solidus temperature in this case? At point A, below point A, the material is completely solid. Similarly, below point B, below the solidus line is this line, the AB solidus line. Solidus line. So point AB represent the melting temperatures of individual alloy. Point A is the melting temperature of alloy A, and point B is the melting temperature of alloy B. The temperature difference between the liquidus and solidus is the freezing range of the alloy. The temperature difference between the liquidus and solidus, while this one is the temperature difference between the melting point of the alloy, is the freezing range of the alloy. So liquidus line is the line which separates the liquid solution from the mixture of liquid plus a mixture of solids. Solidus line is a line which separates the solid solution from the mixture of a liquid plus a solid solution. Alpha is a homogeneous mixture of both the liquids. Alpha is represented for the solid. Below from A, at point A is the composition of solution A is 100% over here, while the composition of B is 0 at this point A. Similarly, at point B, the composition of solution of A at this point is 0% by weight. As we go horizontally from left side to right hand side, the composition of weight percentage of A decreasing, while the composition of weight percentage of B is increasing. So, for example, at 20, the composition of A is 80, while the composition of B is 20. At point 40, the composition of A is 60, while composition of composition of A is 60, composition of B is 40. And similarly, at 80, the composition of B is 80, while the composition of A is 20. At point B, the composition of B is 100, while the composition of A is 0. Binary isomorphous system. What is isomorphous system? Isomorphous system is the complete solid solubility of two components, both in the liquid and solid phases. Suppose this one is the generalized solution, generalized example. Mix two solutions A and B with different melting points are represented in this diagram. Solution A is heated and temperature is plotted in the vertical axis, and composition of A is changed horizontally towards B, point B. Similarly, the composition of B is decreasing from left hand side towards the right hand side, so that at point A the composition of B is 0, as we have discussed previously, and at point B the composition of A is 0. L, it is the complete liquidous solution. L stands for the liquidous, while alpha stands for the solidus solution. Melting point of A is increasing, melting point of B is at this point, is the melting point of B. Suppose if we heat add heat to the solution A, it is solidus until the melting point of A is reached, but at this point the composition of B is 0, and B is still in solid solution until the melting point of B is reached. When the melting point of B is reached, then the solution is converted from the solid to liquid, so that above this point the liquid is completely liquid, or in above the liquidus line, even over here, both the solutions with the composition of with composition at that point and at this specific temperature, both the solutions are in liquid phase, in the liquid region. So these compositions are discussed. At 0, the weight percentage composition of B is 100% at right hand side, and it is gradually decreasing to 80, 60, 40, 20 to 0. And similarly for A, the composition of A by weight is decreasing gradually from 100 to 0 from the right hand side, from the left hand side towards the right hand side. Three phase region can be identified on the phase diagram: liquid solution, solid plus liquid solution over here, solid plus liquid solution over here, and solid alpha. Three phase regions. Liquid S line separates the liquid from the liquid plus solid. Solid S line separates the solid from liquid plus solids. Now if we talk about the microstructure at liquidus point, this is the complete the this is the microstructure of the liquidus point, where the grain boundaries are completely liquid. At this position, the mixture of liquid plus solid, the these are the this is the grain size of the solid solution, while which is surrounded by the liquid solution. The small circles represent the solid grain bodies. This is the microstructure at this point. While it solid is below solid is line. If we study the microstructure at this point, the all the liquid is converted to solid, so a homogeneous phase of the two components is completely converted to solid. All the grains are now in solid position. This is the microstructure. The liquid is grains are converted into solid. This is the microstructure, polycrystal structure of the solid solution. Why we call it isomorphous system? If we have two solutions A and B, if both are mixed with each other in the liquid, if both are completely soluble in liquid phase as well as in solid phase, then we call it a binary isomorphous system. Iso means same. This is the example of a isomorphous system, which is copper and nickel. The If we discuss about the copper and nickel phase diagram of copper and nickel, the melting point of the nickel is the melting point of the copper is 1085 degree centigrade. So the nickel below copper below 1085 degree centigrade is solid until we cross 1085 degree centigrade. Then it start melting. The solution is liquid is above 1085. But at 1085, if we look at this temperature 1085, at this point the nickel, the solution of nickel is completely solid, even at this point, even at this point, and at this point, and at this kind of particular percentage. So 80% nickel solution and 20% copper solution. The mixture of both the solutions is solid at this point. As we cross 1453 degree centigrade, which is the melting point of the nickel, if pure nickel is heated until the melting point 1453 is reached, above this temperature the solution is converted into liquid phase. Even at this phase and at this above the liquidus line, the both the solutions are converted into liquid solution. But if we cool down the temperature from above to below, so that the solution, both the solutions are converted into solid line, at different lines we can find out the composition at various points. Construction of a binary phase diagram. Phase diagrams for binary Li system can be obtained from cooling curves of the system at various compositions of two components. Let us consider two metals A and B. Curve A and B represents cooling curve for pure metal A, and curve B curve, these are the U, V, W, X represent cooling curves of Li A and B different compositions. In curve A, if we look at the curve A, This is the pure pure solution of metal A. The cooling curve is plotted over here, the curve A, while U, V, W, and X, in which different percentage the compositions are mixed with each other gradually. 20% B of at U, at V 40% of B, at W, the curve W, the composition is 60% B. At the curve X, the composition for the curve X, the composition is 80% B. These are mixed with each other so that B is pure solution, at which the composition of A is 0. At X, the composition of A is 20%, while for B is 80% by weight. So cooling curves at different compositions are plotted. This is the other step. Note that the phase diagram show the relationship of phases at equilibrium conditions. This means that the phases present at particular temperature and composition don't change with time once they are plotted at equilibrium. So over here these curves are plotted at equilibrium. So the cooling curves are plotted for A and B and the mixture of A and B in different compositions. So these temperature points are replotted and projected from the cooling curves on temperature versus composition diagram, which we call it phase diagram, by taking temperature on y-axis and composition on x-axis. Composition of the alloys on x-axis. These the cooling curves of temperature versus time is plotted in this method for the general for the phase diagram construction. Then the cooling curves, the temperature points are plotted. Suppose the temperature point for curve 1 is plotted horizontally and we get temperature TA, and similarly for curve 6, cooling curve 6, the temperature, the horizontal line is plotted and we get TB, these 2 points. In between these 2 points, the cooling curve of 2 and 3. 2 is at this point, this is for the line 1, and L2, for the L2 we project it from the curve number 3, we get at this line, and similarly these points are joined. After we get the points, these points are joined, we get a liquidus curve over here and a solidus curve over here. S1 is solidus point 1, S2 is solidus point 2, S3 is solidus point 3, S4, and similarly above L1, L2, L3, L4 are the liquidus points. Later on these liquidus points are joined with each other at different composition, and below the compositions of the cooling curve, each curve is plotted 40% B, 60% by weight of B, 80% by weight of B are plotted, and the phase diagrams are copper silver phase diagram. This is an example of binary eutectic systems. 3 single phase regions: alpha solid solution of iron in copper matrix, beta is the solid solution of copper in silver matrix, and L is represented for the liquid. Alpha is represented for the silver in copper matrix, while beta is represented for the solid solution in copper of copper. Beta is the solid solution of copper in silver matrix. There are 3 two-phase regions alpha plus liquid, beta plus liquid, and alpha plus beta. Where can we locate this? This is the alpha plus liquid solution, this region. This region is the beta plus liquid solution, while this is the alpha plus beta region below the eutectic line. This line is called the eutectic line, while this point E is called the eutectic point, and parallel to this line the temperature is called eutectic temperature. Where is the Solves line? The Solves line separates one solid solution from a matrix of solid solutions. The Solves line shows the limit of solubility. This is the Solves line, the red line. Draw. This is the Solves line. The Solves line shows the limit of solubility. How to find the composition in a two-phase region? Locate composition and temperature in phase diagram. In two-phase diagram, draw the Tai line or isotherm. Note the intersection with the phase boundary. Read the compositions at the intersections. So these are the several steps which we will follow, and we must know about the Tai line and isotherm. We have discussed the Tai line and isotherm in the previous lecture. So without this we are unable to locate the composition in a two-phase region, because the two-phase region is a bit complex as compared to one-phase region. This is your home assignment to how to find out the composition of different elements at different temperatures with the help of Tai line and with the help of lever rule. Usually we use lever rule when we locate the composition and temperature in binary phase region. Tai line and lever rule. Let's do the home assignment over here. A Tai line is drawn on the phase diagram to determine the mass fraction of each element. On the phase diagram, to the right is the line segment, the line segment L to S. This is the Tai line. Tai line is drawn horizontally from the known composition of the element, like O is the known composition of the element, which is WO, weight of O. Sometimes it is represented by O, CO, composition of CO represent composition of the element. So the Tai line, a horizontal line, is drawn from the two boundary conditions, from the known composition of the element, which touches the two boundary conditions. One is the liquidus, the other is solidus. So over here, the L at point L, the liquidus line is touched. Over here, the solidus point is touched. This Tai line is drawn horizontally at the composition's temperature from one phase to another phase. Over here the line is drawn from the liquid phase to solid phase at the same temperature. So Tai line, we have the same temperature but different compositions. One is for the liquid phase, WL, or weight of the liquid, and for the solid phase we draw a vertical line from point S to downward, which represents WS. So percentage weight of B is shown horizontally, temperature is vertically for general phase diagram. Tai line and lever rule. The lever rule is a rule used to determine the mole fraction or the mass fraction of each phase of a binary phase equilibrium phase diagram. It can be used to determine the fraction of liquid and solid phases for a given binary composition and temperature that is between the liquidus and solidus line. In an alloy or a mixture with two phases alpha and beta, which themselves contain two elements A and B, the lever rule states that the mass fraction of alpha phase is, this is the generalized formula, mass fraction WA for the solidus, WB minus WB beta divided by WB alpha minus WB beta, where WB alpha is the mass fraction of element B in alpha phase. WB beta is the mass fraction of element B in beta phase. This is if the two different true phases. WB is the mass fraction of element B in the entire alloy or mixture, all at some fixed temperature or pressure. We will simplify this formula further by solving some numerical examples, and we will explain it further in the upcoming slide. Lever rule example. The lever rule states that the relative amount of each phase is directly proportional to the length of the opposite lever arm. The relative amount of each phase is directly proportional to the length of the opposite lever arm. The line OMP in this general phase diagram, the line OMP has two arms, OM and MP. This OM and MP. While this is the lever, the middle point M is the lever between these two segments, which intersects the liquidus point. This is the liquidus point O and solidus point is P. Intersects the liquidus curve and the solidus curve. According to the lever rule, the length MP touching the solidus is proportional, touching the solidus line, the MP, the MP is touching the solidus curve is proportional to the amount of liquid present at M, and the length OM touching the liquidus curve is proportional to the amount of solid phase present at M. So we will relate that proportionality with each other to find out the solidus curve and the weight, the amount of liquid phase and amount of the solid phase. So amount of liquid phase at point M, amount of liquid phase at point M is equal to MP divided by OP. MP, that from point M to P divided by OP, while amount of solid phase present at M is equal to solid phase. We will start it from the solid point. For the solid phase, we will start it from the solid point. For the liquid phase, we will start from the middle point to the liquid point. The rest, the division will be the same, OP. Like for the solid phase present, the amount of M will be equal to OM divided by OP. Will be multiplied with the 100, so that we can get the percentage amount. This proportion, the composition below the point O is 20 which percent of the element from the left hand side, which will be known to us. This composition below point O will also be known. Similarly, the known composition at point M will also be known. We are only interested to find out the amount of liquid phase and amount of solid phase at this point M. What is the composition of what is the amount of liquid and what is the amount of solid phase in the mixed boundary L plus alpha region. So in order to calculate this, let's put the values in this formula, in these two formulas. MP is equal to 90 minus 40. MP 90 minus 40 divided by OP. OP is equal to 90 minus 20. Similarly, OM is 40. OM, this line OM is 40 minus 20 divided by same OP, 90 minus 20 multiplied by 100. In engineering materials written by Celester is the same example for the nickel copper nickel phase diagram. Some examples are given. We will explain this further to